Hello. In this video I'm going to discuss passive vibration damping, and I've got a link on GrabCAD over here where you can download the SolidWorks files that I'm going to use in this presentation, and the motion studies are already set up in that. So if you have SolidWorks Premium and activate SolidWorks Motion, you can try to run these analyses yourself quite conveniently. So I'm going to have a look at passive vibration damping, which means that a mass is moving because of an input that is caused by something else. In this case, this moving platform via a spring causes movement of this mass. So I'll play this animation over here, this simulation. So this is what I'm going to analyze. I'm going to show these analyses later on. First I'm going to go to a presentation. I've got it over here. So this, for example, could be a schedule of a passive vibration damping, so a mass that is moving according to a profile that is caused by a rod, and via a spring and a damper the movement of the rod is causing forces on the mass. So then it's always good to create the free body diagram. You should always do that when doing dynamics, and I prefer to write all the force arrows in blue and then the acceleration arrow in red, multiplied by the mass, so then it should be convenient. The sum of all forces, which is the sum of all blue arrows, should be equal to mass times acceleration, and then you've got your equation of movement already. So I've written that over here, and I've done the easy version of the Laplace transform. So the Laplace transform can be quite complex mathematically, but the simple version is just to replace every differentiation, so every dot above a variable, by an s, which I've done over here, and then you get the transfer function as a function of this value s, which is a complex number. So to understand that, you should have already had education in complex numbers. So I've written it down over here, and now I can see that this formula, this transfer function, is exactly the same as it is in active vibration damping, and I've done a video on that as well. You can find it on the same YouTube channel. So that makes creating all the next sheets very easy, because it's exactly the same as the previous ones. I've created a bode plot with MATLAB, and you can also get free apps, for example, in the App Store of, at least I know that Android has them. Probably Apple will have them as well. So you can find apps, but you can also find websites that will draw these bode diagrams. If you have MATLAB, then it's most convenient to do it with that, because you can create an absolute scale, not logarithmic, which I find convenient because I don't have to recalculate everything. So here there are four plots, and the blue one has a damping of 0, which means that the response in the natural frequency will be infinite. So the blue line, you can hardly see it over here, goes to an infinite value. And this is the transfer function of a plot of a damping constant of 5 Newton per meter per second. And that's the situation I've also created in SolidWorks Motion. So if I go there, then I can see here there are 3 studies set up, and these 3 studies correspond to these 3 values in the graph over here. So let's first have a look at the low frequency. It's 0.8 Hertz, and when going to SolidWorks, we should calculate them in hertz. At least that's what. So how it's set up right now, you can change these units, but at least you have to pay attention to them. So you see an input of 10 centimeters, 10 millimeters at a frequency of 0.8 hertz, and then when running this simulation, it's running at a quarter of the speed, a quarter of the actual speed. So I've slowed it down a little to be able to see what's going on. And now it's easy to see that the input should be equal to the output, because of this low speed, the mass inertia and also the damping is neglectable, because the speeds and the accelerations are so low. So the only thing that really matters is a spring constant, and then you can see that the output is exactly the same as the input, which means that the transfer function should be 1, which you can see over here as well. It starts as a value of 1. Then when I go to the natural frequency, the input divided by the output should be a factor 4.5. So I set it up in this study, and when I'm running this analysis, you can see we're in the natural frequency. The spring is exactly in its natural frequency. If the damping would be 0, then the response would be increasing forever in this simulation. But when I look at the spring here, you can see I've activated the damping of 5 Newton per meter per second. And now I can look at the output, which should be 4.5 times bigger as the input, which is not that straightforward because I started at the sine not in the middle but at the lowest point of the sine motion of the displacement. You can change that, but I thought it would be good to show what happens when you run into such a situation. Then the plus value is not exactly the same as the minus value, and I've done the calculation here on my calculator. So when you add 28 and 18 and divide them by 2, you get a value of 23. 23 of total movement as the output, so 23 one way and 23 millimeters the other way. And when I look at the input, it goes 0.005 one way and 0.05 the other way. So 0.05 times the value of my transfer function, which is 4.5, gives a value of 23, which is exactly the output divided by the input. So pay attention to these graphs and also to the input. So the input is 5 millimeters, the output is 23 millimeters, which corresponds very closely to this value of a factor of 4.5 that I see here in my graph. So the more accurate you would read that value out over here, the more accurate you could also predict the input divided by the output. And then when I go to the last analysis, so here I've got a maximum phase shift at a value of 6 Hertz. That's what I've created here in SolidWorks simulation, SolidWorks Motion analysis as well. So 6 Hertz is 40 radians per second. And then when I run this simulation, when I click on the spring, I see the spring in the image as well. This one is running on 1/4 of the speed as well. So now if I really want to see what's going on, maybe it's better to run at 1/10 of the speed, because then it's more easy to see what's going on. It's a bit slower now. And according to the graph, the phase shift should be maximum right now, which you can see here. When this one is going up, this one is going down. So it's not exactly that way, but it's very close to it. And that's what I can see in this graph too. When I hold a window next to it like that, you can see when this one is at the lowest value of this graph, this one is almost at its top value, not exactly, which I can see in, sorry for the switching, which I can see in this lower graph as well. It's close to minus 180 degrees, but not exactly, which I can see in this graph. And I can see it in SolidWorks Motion in the movement, and I can see it in SolidWorks Motion in the graphs as well. So that looks very convincing. So it looks like I've done the right simulation for the right MATLAB analysis. So that was what I wanted to say about the passive vibration damping. Thanks for watching.